Hello. Hello, welcome. So today's webinar will be led by David Vaccaro. Hello, David.
How are you?
Hello, very good.
I've got a little bit of a problem that I've left my stylus in work, so I'm gonna have to write. I'm gonna have to write with my finger, so it'll be a little bit messy.
It's all right.
Yeah.
I once wrote with my mouse, and that was.
Oh, I might try. I might see if that's better. Yeah. I'll see what works. I'll see what works better. Yeah, proper physics sheet this time. Delta functions. Shall I get started, or shall we wait for others?
Yeah. I think that's.
I've not followed the physics sheet so much. Have they evaluated the Gaussian integral ever? Do they know why the integral is root pi?
No.
No. Okay, super. Okay, well, I'll start with that. That seems like a good place to. Or you just need to make me host, I think.
Oh yes.
What I'm going to do is I'm just going to close all my windows apart from this one.
Okay, you're a host now.
Super. This is Zoom, isn't it? Okay. Okay, good evening, everybody. So, whoops. As I mentioned, I'm without my stylus, so apologies if my writing is a little bit poor. I'm going to start with evaluating this Gaussian integral. And the first observation I'm going to make is, how would we find the volume?
Sorry, are you sharing?
Oh, am I sharing?
It doesn't seem like it.
Oh, sorry, I didn't do the last piece. So what is the volume? Actually, I'm just going to have to write, I'm just going to have to speak rather
We
than...
have just a quick introduction of the Gaussian integral itself. They haven't seen the sheet yet.
Oh, right, so, okay.
Yes.
So the Gaussian integral that we're going to look at is the integral of this function, y equals e to the negative x squared. So a good thing for you all to do is to think what that function looks like. So hopefully you can convince yourself that x squared is always positive. So we're always going to be taking the exponential of a negative number. And so the exponential of a negative number is going to be less than 1, or it's going to equal 1 when x equals 0. As x increases, x squared increases. So for large values of x, we were going to be taking it's the reciprocal of e to a large positive number. So the function is going to tend to 0. So the function y equals e to the negative x squared has got a maximum value of 1, which it attains at x equals 0. It then decays either side of 0 and goes down to a horizontal asymptote of 0. Now, Vlad said that you've never seen the Gaussian integral before. I bet that all of you have seen this function before. And indeed, I bet in one way or another, you've all integrated it before. Where do you think you have seen and indeed integrated this function y equals e to the negative x squared in your travels? I'll wait to see if anyone puts that into the chat. Well, maybe a slightly varied form of this function, but this function is very, very closely related to something that you've all seen. How would we describe the shape of it? Well, it's shaped like a bell. And what's the famous bell curve in mathematics? That's the normal distribution. And we'll talk, the normal distribution is slightly altered to have an overall integral of 1. Now, the first thing we're going to do is we're going to try and find the Gaussian integral, which is the area under this curve. Now, the first thing it should be relatively straightforward to convince yourself of is that that integral converges, because e to the negative x squared decays faster than e to the negative x, and the integral of e to the negative x we can integrate without any problems. Now, what is a very interesting fact is that you cannot integrate this Gaussian integral using the functions that you know about, using the exponential functions, sine, cos, tan. You can integrate it, but you need a whole new function. You need a new button on your calculator, essentially. Okay. What we're going to do now is we're going to actually evaluate the integral, and I'm going to show you how we can show that this green area is the square root of pi. And the first observation, the first sort of step in that journey is, and it seems that this is sort of unnecessarily complicated, but the first step of this journey is what I'm going to do is I'm going to imagine that we take a function of two variables, x and y, and we consider that to be the height of the variable z. So my height z is a function of x and y. So this is going to be a three-dimensional object. Okay, so this is my x-axis. This is my y-axis, and then we have some surface. Okay. That would be difficult to draw even if I had a working stylus. Without a stylus, it's even more difficult. But it's like a picture of a sort of mountain range or so forth. I'm sorry, my dog is barking. I do not know why. Now, the first thing we're going to think about is how could we find the volume under this curve? So let's consider finding volumes the way one might normally find volumes. Let's slice this up into sort of infinitesimal pieces. And what I'm going to do is I'm going to fix which way round shall I do it? I'm going to fix a value of y. And then I'm going to take a slice at that value of y across all my x values. Okay, so let's say that x ranges from a to b and y value range from c to d. Okay, so this slice that I've taken, it's very thin, and its thickness is going to be dy. Okay, and so I've got this little slice. So I've got this mountain range, and then I've taken two vertical cuts close together. Now, what's the volume of that vertical cut? Now, in profile, the green area is the integral from a to b of f of x with y fixed. And then I integrate that with respect to x, treating y as a constant. So that's the area under the kind of flat curve, so that just the green shaded area. And then to get the volume, I multiply by the thickness. So multiply it by dy. So that's the volume of that little thin slice. Now then, to get the total volume, I need to then add the volume of all of those little slices. And the mathematical operation to do that is to then take the integral across the different values of y. So if I now integrate with, if I now integrate my y values from c to d of the integral from a to b f of x y dx with respect to dy, I get the volume. And it's worth noticing here that I treat this y just as if it's a constant. Okay. Can I just check everyone's following? Does anyone have any questions about that? Why this volume is a double? Why this volume is a double integral? If you understood that argument, or you're happy for me to carry on, put a thumbs up. If you've got any questions, then let me know. Okay, we've got a thumbs up, a couple of thumbs up. Good. So what I'm going to do next is I'm going to use this result to find the volume of under the following curve, which is my z is going to be e to the negative r squared, where r is the distance of a point from the origin. So r is the square root of x squared plus y squared. So alternatively, I could write z equals e to the negative x squared plus y squared. Now, before I move on and do this integral, I think it's really important to try and just visualize what's going on. So try and think in your own minds at this point what this surface will look like. And while you're trying to visualize that, I'm just going to pull up graphing software, and I'm just going to sort of look at this 3D Gaussian. So plot 3D, and then I'm going to do e to the negative x squared plus y squared, and I'm going to do x from negative 5 to 5, say, and y from negative 5 to 5. Oops. I forgot to put the brackets in. Oops. Brackets in the wrong place. Third time lucky. Okay, so what we have here is we have a kind of a little bit like a normal distribution, but now in 2 dimensions. Okay, so it really is like a It really is like a bell. Okay, and the contour lines of this are concentric circles because the height of the curve is determined by the distance away from the origin. So if I was going to sketch this, curve, it's a bell curve, and then at a distance r from the origin, it's at a constant height. Okay, so the distance r from the origin, it's at a height e to the minus r squared height. Now, let's find, what I'm going to do now is I'm going to find the volume that is contained within this shape. So you can see as r gets big, it becomes really flat. So it becomes essentially flat. So it's just like a little indentation. So my question is, how much water could I pour into that? Could I pour into that hole? And I'm going to do this integral in two ways. The first thing I'm going to use is I'm going to use the two-dimensional formula that I had before. So I'm just going to take the integral from negative infinity to infinity of the integral from negative infinity to infinity of e to the negative x squared minus y plus y squared dx. And then I'm going to integrate that with respect to dy. But I can do something here. I can use my laws of exponentials to write this exponential of a sum as a product of exponentials. So I can write this as the integral from negative infinity to infinity of e to the negative x squared e to the negative y squared dx with respect to dy, integral from negative infinity to infinity. But now I can, because I'm treating y like a constant, I can just take that constant outside. So what I get is the integral from negative infinity to infinity of e to the negative y squared, and then the integral from negative infinity to infinity of e to the negative x squared dx dy. Now, I told you earlier that this area under this Gaussian integral, this green area, integral from negative infinity to e to the negative x squared, you can't do by classical means. So I'm just going to call this green area I. So what I can do is I can say that this integral here is the area under my Gaussian curve. So this is just I. I can take that outside as a constant. But now I just get an integral of just exactly the same type. I just get an integral of e to the minus y squared dy. And the letter has changed, but this is still the area under a normal distribution. So the volume under that Gaussian curve is I squared, where I is the area under the 1D Gaussian curve. I'm just going to pause at this point and just check that everybody is still happy. If you're still happy, then have a thumbs up. If you've got any questions at this point, then put them into the chat. But if you're happy to continue, put a thumbs up. Excellent. We're getting thumbs up coming. Let's return now and find the area, the volume under my two-dimensional Gaussian in a slightly different way. So I'm just going to redraw the curve. So here's my curve. And I decided that the contour, which was a circle of radius r, is at height e to the minus r squared. And what I'm going to do is I'm going to calculate the volume underneath that ring. Now, if we consider that ring, we could picture a little circle, a circle of radius r, and then I'm going to make it very, very thin, and its thickness is just going to be dr. And then underneath that ring, so you're getting like a little pipe. You've got a pipe which is of height e to the minus r squared, and of thickness dr. Now, what's the volume of metal in this pipe? Well, the cross-sectional surface area is just this circle. Now, if you were to roll the circle out, you would get a length which was the perimeter of the circle, which is 2 pi r, and of thickness dr. So the area here is 2 pi r dr. And then that area is extended down the pipe, the height of e to the minus r squared. So that's the volume underneath this thin contour. And obviously the volume is then made up of lots of those pipes. So the total volume is the integral from negative infinity to infinity of 2 pi r, sorry, not r squared, r e to the minus r squared dr. But here we're much luckier because we've got an integral, that we can do. Okay, so if the radius doesn't go from negative infinity, the radius goes from 0 to infinity. If I was to differentiate e to the minus r squared, I would pick up a factor of negative 2r. I only get a factor of r, so I want a minus sign, and then I take the pi outside. And so using this, this integral, so calculating the volume this way, I've got an integral that I can do. Okay, so the volume is pi, and then I've integrated it as e to the minus r squared. If I substitute in my upper limit of infinity, I just get 0. If I substitute in my lower limit, I get pi. So the volume of that cone, that infinite bell, the volume here of this spike, so this two-dimensional Gaussian, is pi. But what we saw is that that volume is also the square of the one-dimensional Gaussian integral. So we're now there. We've got that the Gaussian integral I squared is equal, the Gaussian integral squared is equal to pi. So the Gaussian integral is equal to the square root of pi. Okay, and that result is quoted on your sheet. But I thought it would just be quite nice to actually prove it, here. Okay. Challenging piece of maths. Does anyone have any comments, queries, questions, or are people happy for me to carry on at this point? Oh, so someone said, I got lost from after the I squared bit. Could you quickly summarize? So what I did was I found a different way of finding the volume under the curve. So what I did was I did a horizontal cut. So I got a circle. And then that circle is at a constant height of e to the minus r squared. And then if I made that circle just have a little bit of a thickness, so dr, okay, I could then find the volume under that kind of pipe. Yeah. So imagine this whole 3D shape. I could get one part of the volume by just doing the sort of spike in the middle. Then around that, I could put another little pipe, then another little pipe which is a little bit shorter, then another little pipe which is just a little bit shorter still. So I'm cutting it into concentric rings. And the volume of each ring is the cross-sectional area, which is 2 pi r dr. And so that's the area of this circle, which is the perimeter times dr, multiplied by the height, which is e to the minus r squared. So the volume of the shape could be obtained as this integral. And this integral is one we can do. And we get out that the volume is pi. But earlier on, we showed that the volume is the Gaussian integral squared. So we got I squared equals pi. Okay. How is that? Is that, yeah, there's, okay, good. Okay, next question. When do we get a Gaussian integral? So I'm a probabilist at heart, so I'm going to consider the following process, and I'm just going to do it in one dimension. I know you're sort of physicists, so you would naturally do this in 3 dimensions, but I'm just going to consider what's called a Brownian motion, so, or a diffusion. So this is what we would imagine that a particle would do if it just moved randomly. So what I'm going to do is I'm going to imagine that we've got a little particle and it starts here. And in each time interval, okay, it takes a small step, either to the left or the right. And in the next time interval, it does either a small step to the left or to the right. And in the next time interval, it does either a small step to the left or the right. And I'm going to imagine that it does capital N steps per second. Okay, so how many, let's think about where it is at time t. Okay, so it does capital N steps per second. So it does x1 plus x2 plus dot 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 xn. And this is the first second. Okay, then in the next second, it does another n steps, and so on. Now, in a diffusion process, well, in a real sort of diffusion process, we would imagine that n would be large. And if we add a large number of independent random variables, we would expect this to be normally distributed. So what we would have here is a random variable, let's call it z, which is centered on the origin, so of mean 0, and then of some variance, and I'll just call that sigma squared. So that sigma squared is the variance in a 1 second time interval. But in the second time interval, we're adding the same number of steps. So we're just going to add a second normal random variable, which is also independent, which has got the same variance. And over t seconds, we would add t of these. Okay, but we know if we add normal distributions, then the variances add. So the distribution of the particle, we would expect to be normally distributed with a variance of sort of sigma squared per second. So after t seconds, so at time t, the position would have distribution normal, mean 0, and then variance sigma squared t. Okay, and I said earlier that the normal distribution wasn't quite e to the negative x squared. The density function, you make it so it's equal to 1. So the density of a normal distribution is actually the density function is scaled to have a total area of 1. So a standard normal random variable, so n01, the distribution function is 1 over root 2 pi e to the minus x squared over 2. But then if I increase the variance to sigma squared t, this density function changes. So this is the density function of Brownian motion after time t. Is 1 over root 2 pi sigma t e to the minus x squared where am I? Yeah, over x squared over over sigma squared t. Over sigma squared t squared. Okay, so let's just investigate this a little bit. Excellent. Okay. Okay, so what this gives me, this gives me the probability density function of where I would find a particle under Brownian motion when I change time. So what happens as time increases, while the most likely place to find the particle is where it started, as time increases, because it diffuses, because it moves around, it becomes more likely to find it away from the origin, because I've given it plenty of time to diffuse away. However, when time is, when the diffusion hasn't been within the early stages of the diffusion, so when time is small, it becomes much more likely to find the particle close to the starting point. Okay, so after just a millisecond, you would expect to find the particle exactly at 0. Okay, but as the time increases and the variance increases, you get this wider bell curve. Now let's see if there's any questions in the chat. So some good questions. So first question is, why do the variances add? Okay, that's just a result from probability theory. Okay, that if you've got two independent random variables, and these don't have to be normally distributed, then the variance of x plus y is just equal to the variance of x plus the variance of y. So the idea with our Brownian motions is that are lots of independent steps by the central limit theorem end up being approximately normally distributed. The variance of the steps across each interval of, let's say, of length a second is the same, because, you know, if it's 1,000,000 steps over the first second, it'll be 1,000,000 steps over the second. So the variance will just be the same. And so the variance is proportional to time. Okay, so if we do have a Brownian motion, so this observation here is saying that if I do have a Brownian motion, if I do have a diffusion, then the variance is proportional to time. And that's just because the variance over each kind of second-long interval is the same. So that answered one of the questions. Oh, can you explain how you get the probability density function again? Okay, so broadly speaking, this integral e to the minus x squared can't be a probability density function because the integral isn't 1. So I would need to divide by 1 over root pi. And I won't do the calculation now, but it turns out that this wouldn't give a normal distribution with variance 1. The variance would be slightly out. It turns out that this integral is the probability density function of the standard normal. What happens when you so this is the PDF function of the standard normal. When you change the standard deviation of a normal random variable, you're just doing a horizontal stretch by a factor of t. Okay, so you just get the same function but stretched out and then corrected to get a unit area. So if the standard deviation becomes t, this becomes the PDF. Okay, what you can see immediately is that the maximum will occur when this exponential on the numerator is 1. So the maximum value of the density function is 1 over root 2 pi sigma t. Okay, and as t becomes close to 0, that spike therefore gets taller and taller and taller. Okay, and obviously what that function represents is how likely you are to find the particle close to that point. So when time is small, you're much more likely to find it at a point close to the origin. When time becomes big, it's much more uniformly distributed. And after a long period of time, so when t is large, you're just as likely to find it anywhere within the room because it's just diffused and we've just got a uniform distribution. Okay. Any more questions about that bit so far? Okay, the next question is, what happens in the limit when t goes to 0? So if you look at this function, so this this density function of my normal distribution, when t becomes very small, minus x squared over t squared, that becomes very large because I'm dividing by t squared. So, and if I divide by a small number squared, I get something large. So the function becomes almost 0 everywhere. Okay, so my plot here is essentially 0. But why isn't that the full story? When t is very small, it looks like the density function is just 0 everywhere, but the particle's got to be somewhere. So when t is very close to 0, where is the particle? Okay. So when t is very, very, very close to 0, what my computer is not plotting is this enormous spike at 0. Okay, so in fact, when t is exactly 0, the particle is with probability 1 at 0. Okay, now this is something which will make the mathematicians come out in a cold sweat, but what the physicists define is the physicists define this function, they call it the delta function, they call it delta x, and it has two properties. Okay, when x is not equal 0, delta x is just 0. But the other property of this delta function, which the physicists defined, is they say that the integral of delta x dx from -infinity to infinity, they say it's equal to 1. So so it's a curve which is 0 everywhere, but then still has an area of 1, and that area of 1 is carried entirely by a spike at 0. Okay. And mathematicians who don't like that, what they say is that the delta function is the distribution which is the limit of the normal distribution when the variance goes to 0. A little bit of a interesting concept. Does anyone have any questions? Does anyone have any questions about that spike function? Yeah, so someone said here, because at t equals 0, it's at 0. So this is equivalent to the density function of a random variable which is not which doesn't have a continuous distribution, but which has got a sort of point mass. So a particle which is for sure at 0. Okay, let's have a look at some of the questions on the sheet. Okay. Oh yeah, this is nice. Well, I think it's easier to explain just with the normal with the normal interpretation. So what's this integral? Okay, well, the way I conceive of this integral is I think of this delta x as being the probability density function. So this is the PDF for a particle which is just at 0. Okay. Now, obviously, if we now do the integral of fx multiplied by a PDF, then that just gives me the expectation of f of my random variable. Okay, but if I'm taking the expectation of my random variable, in this instance, my random variable is just at 0. So this integral is just f of 0. Okay, the other way of thinking of this integral is thinking back to my dx as being a spike. Okay, so if I take my spike and I multiply by fx, my delta function at most points is just equal to 0. So when I multiply by fx, I just get 0, so it remains 0. But my spike, if I multiply it by fx, just becomes f0 times as tall. But previously, my spike had an area of 1. When I make it f0 times as tall, the area of my spike becomes f0. Okay, so this is all, we can almost regard this as a definition of the delta function. So here, this spike function at all points other than 0 is just killing f, so that nothing contributes to the integral, and then at 0, it's just a spike of height 1, so it just contributes a total value of 1 to the integral, which you then multiply by f of 0. Okay. Does anyone have any questions? Does anyone have any questions about that? Okay. There's theoretical material in the sheet. There's problems to do. Are people happy for me to move on and look at the next thing which is on the sheet, which are these, well, the Fourier transforms. So if you've got any questions, put them into the chat. If not, put a thumbs up and we'll move on to Fourier transforms. Okay. Excellent. A thumbs up. Right. So let's. Actually, what I'm going to do, I'm going to again take a little bit of a, I'm just going to take a little bit of a sort of probabilists view of Fourier transforms. Yeah, let's take a probabilist's view of Fourier transforms, and I'm also, if there's time, I'm going to prove the central limit theorem. So what I'm going to start with is, let us take so let us imagine we've got a random variable, let x be a random variable with density function, so with PDF f of x. What would I need to do? And I think you should put this into the chat. What would I need to do to get the exponential, the expectation of e to the I theta x? what calculation do I do in order to get the expectation of a random variable? Oh, right, yeah. Desmos won't like the I because the I is a complex number, so Desmos won't like it. Desmos, what you could do on Desmos is you could get the expectation of just e to the theta x, which is not called a Fourier transform, but which is called a Laplace transform. But I'm going to stick with e to the I theta x. Well, how do you go from a PDF to an expectation? What do you do? Yeah, you do the function, you do the integral of the function times the density function. So you do the integral from minus infinity to infinity of e to the I theta x multiplied by f of x dx. And because we integrate with respect to x, we end up with a function of theta. Okay, so I'm just going to do an example. So let's take what random variables do we know? Let's do the PDF of an exponential distribution with parameter lambda. And then let's do the integral of that PDF times e to the I theta x, x from 0 to infinity. Actually, Mathematica is trying to be too clever for its own good. So the PDF of a exponential random variable is lambda times e to the lambda x. So let's just do the integral of e to the I theta x, and then multiplied by e to the negative x lambda times lambda x from 0 to infinity. And I want, sorry. Sorry, I was trying to do it in Mathematica just because I was struggling to write. So for an exponential random variable, we've got the integral from 0 to infinity of my PDF, which is e to the minus lambda x. And then we multiply that by e to the I theta dx. And then we've got an x here. So now we get the integral from 0 to infinity of lambda e to the I theta minus lambda x dx. But we know how to integrate exponential functions. Yeah, we just need to divide by the I theta minus lambda. So we get lambda I theta minus lambda e to the I theta minus lambda x evaluated between 0 and infinity. When I substitute in the infinity, because lambda is bigger than 1 and e to the I theta is just a complex number of modulus 1, I get 0. So that term disappears. Then I substitute in the 0 with a negative. So I just get lambda over lambda minus I theta. Okay, so this object here is the expectation of e to the I theta x when x is an exponential random variable. Okay, now, what is difficult to believe at sort of first glance is why, or alternatively, it's the sort of function f via this integral has turned into this function of theta. So what we've done in this operation is we've gone from a function f of x, so a function of x, and then what we've done is by doing this integral, the x's kind of are the variable of integration, so they go away. And what we end up with on the other side, so splitting out of this transformation, we've got, and I'll write it the normal way, we've got a sort of function curly f of theta. So this process is called a Fourier transform, and this is what you will be doing in the sheet. And what the Fourier transform does is it turns a function of x and it spits out a related function of theta. Okay. And I'll explain a little bit in a moment in the probability setting why this function of theta turns out to be useful. But before I proceed, because it's quite a strange concept, does anybody have any questions at this point? Are you all broadly happy, at least with the kind of big picture, that the input is a function of x, the process is an integral, and the output is a function of theta? Right, let's look at how this function of theta might be useful. So what we've shown is that if x is exponentially distributed with parameter lambda, then my Fourier transform, which is the expectation of e to the I theta x, is equal to lambda over lambda minus I theta. Okay. What is another way of writing e to the I theta x? How else could I write e to the I theta x? Put it into the chat. So how else could you write an exponential function? So an exponential function can be written as, by Maclaurin's expansion, I could write this as 1 plus I theta x plus I theta x squared over 2 plus I theta x all cubed over 3 factorial. Okay, what happens when I take expectations? So what can I say is if I've got random variables, what's the expectation of a sum? So the expectation of a sum is the sum of the expectations. So what we've got here is we've got the expectation of 1, which is just 1. We've got the expectation of I theta x, which is I theta times the expectation of x. Then we've got I theta x squared, so that's a minus theta squared x squared over 2. And then we've got a minus expectation, minus I theta cubed expectation of x cubed over 3 factorial. But what we have here, okay, this is a Maclaurin expansion. So this is the Maclaurin expansion of the Fourier transform. But we know what the Fourier transform is. We know that the Fourier transform is lambda over lambda minus I theta. So let's call this curly f of theta. But what's the Maclaurin expansion of f of theta? Well, it's the Maclaurin expansion is f of 0 plus f dash of 0 theta plus f double dash of 0 over 2 factorial theta squared, and so on. So let's look at what we've got. So here we have the Fourier, we can see that the Fourier series of, the Maclaurin expansion of the Fourier transform has got coefficients which are the expectation of x, the expectation of x squared, the expectation of x cubed. Whereas down here, we've got that the Maclaurin expansion of the Fourier series is just given as normal, involving, the first, second, and third, you know, the 0th, 1st, 2nd, and so on derivative of the Fourier expansion. So what that means is I can use this Fourier transform to find these expectations. So let's do that. So actually, I'm going to get the computer to help me here. So series lambda over lambda minus I theta. Okay, so what we've got here is the Maclaurin expansion of so what we've got here is the Maclaurin expansion of the Fourier series. Let's see. So what we can see, let's compare the two series. So they both start with a 1, that's good. The term up here is I theta over lambda. The term here is I theta expectation of x. So just comparing the two, the coefficients need to be the same. So we've got that the expectation of x is theta over lambda. Let's look at the next coefficient. We get negative theta squared over lambda squared by looking at the Maclaurin expansion of the Fourier series. Whereas down here, we've got as our coefficient negative theta squared expectation x squared over 2. So if we compare the two coefficients and make them equal, we've got that the expectation of x squared must equal 2 over lambda squared. And I'll just do one more. The coefficient of theta cubed is minus I theta cubed over lambda. Whereas down here, we've got it as minus I theta cubed expectation of x cubed over 6. And then if we simplify, we get that the expectation of x cubed must be 6 over lambda cubed. Let's just see if this is right. So let's do expectation of, let's do the last one, x cubed. Where x is distributed, exponential distribution lambda. So we get 6 over lambda cubed, which is right. And hopefully you've spotted a pattern that the pattern goes, the expectation of x is theta over lambda, then 2 over lambda squared, then 6 over lambda cubed. With a little bit more work, you shouldn't be so surprised that the next one is 24 over lambda 4. And if we were to get the general Maclaurin expansion, we would get that the expectation of x to the n is n factorial over lambda to the n. Okay, so a recap. And this is in the context of probability. Okay. So in the context of probability, if we were to calculate the expectation of the exponential function, then we could use Maclaurin's expansion to see that that expectation has coefficients which give me the expectations of the power of the random variable. So this is a powerful function. So e to the I theta x can be used to tell me all those expectations. So it's got a special name. It's called the moment generating function because it generates all those expectations of powers. Okay. So in the context of probability theory, this object, this expectation, is an important object to calculate. But this expectation is given by an integral, and it's given by integrating the density function multiplied by this exponential. Okay, and so this operation, which you'll meet time and time again in your studies, in maths and in physics, starts with a function of f, spits out a function of theta, and this function of theta has encoded in it, encodes useful information about f. And from the probabilistic point of view, it makes it easy to calculate the expectation of x to the n. Okay, so recap from your sheet. Okay, so this transformation is the Fourier transformation of a function f into a function f hat. And what the body of the sheet is to actually do some of those calculations and find those Fourier transforms. What I've tried to give you here is a little hint that the Fourier transform turns out to be something important. Okay, does anyone have any questions about what I've said? Okay, so let's just do one of the example problems. Actually, I think this is a good place. I think this is a good place to leave it. So what I would recommend you do is to have a look over the sheet. Okay. But the main takeaway message is that the delta function is the limiting object of what happens to a normal distribution when the variance goes to 0, and that those normal distributions become a spike, and the delta function corresponds to a probability distribution function where all of the probability is concentrated on 1. And then the second thing that we looked at is the Fourier transform. And me being a probabilist, I showed you that one of the uses of a Fourier transform via Maclaurin expansions is it enables us to find it's an easy way of finding the expectation of the random variable, of its square, of its cube, and so forth. Okay, so I hope you enjoyed that, and I hope you enjoy having a look at the sheet. Does anyone have any final questions, comments before we go? Super. Okay, I hope you all enjoy the rest of your evening. Bye-bye, everybody.